Now we're going to talk about oxygen transport, meaning how it's moved through the body. So we have oxygen that's carried in blood in two different ways. Most of it is going to be bound to that iron atom in hemoglobin of the red blood cells. Some, about 1.5%, is actually dissolved in the plasma. So it's just in solution and it's not attached to the iron of the hemoglobin. Each hemoglobin molecule made up of, again, 4 polypeptide chains. So four kind of chains, the alpha and the beta. There's 2 alpha, 2 beta. Each has an iron molecule in the middle of it. So each has the polypeptide chains is the globin of it. And then the heme part is the heme group, or that pigment. In the middle is that iron atom. So if you have 4 iron atoms, each hemoglobin molecule can carry 4 oxygen molecules because that's where the oxygen attaches to. If it's oxygenated, meaning that there is an oxygen bound to each one of these iron molecules in the heme unit, then it's called oxyhemoglobin, or it's called oxygenated. When it releases the oxygen, because remember this is weakly bound, you want it to be able to stick and unstick, so it's like Velcro, it's pretty easy. So when the oxygen is released, it's called reduced, or it's deoxygenated, meaning you got rid of it. So look at it again in the lungs. Coming in the pulmonary capillaries, we have hemoglobin and oxygen separated, and then they attach. And a lot of times it does involve a hydrogen atom, proton. And then in the tissues, we want the opposite. So you want it to separate and oxygen be released. So looking at the partial pressure of oxygen, and this can be either in solution, so this is looking at our differences, so it can either be partial pressure in the alveoli or partial pressure in the blood. This is going to determine how much of the oxygen can attach to the hemoglobin. So we look at what we call hemoglobin saturation. How much of the iron atom in that middle of the heme unit has an oxygen? So if we look at it, when we have a partial pressure of 105 millimeters per mercury, we say hemoglobin is saturated. That means there is an oxygen that will attach to every iron atom that's in that heme pigment on the hemoglobin. So each one of the hemoglobins has 4 oxygen molecules attached to it. Why is it saturated? Well, you can't carry more than 4. There's only 4 iron atoms, so only 4 oxygen molecules can attach per hemoglobin molecule. So if there's 4 oxygen molecules per hemoglobin, no more can happen. So we look at it with oxygen hemoglobin saturation curve is a graph, and it can look at how much of our hemoglobin is saturated, meaning how much of our hemoglobin has all 4 of its irons occupied. And we can look at it, how it changes based on the partial pressures of oxygen. So what we can look at is what we say is there's an increased affinity, or there's an increased desire for oxygen to bind to hemoglobin. So hemoglobin has a higher desire to get all 4 oxygens that it can. So it really just wants to be full. So If there's only a couple oxygens bound to it, then its desire is higher. Obviously, it has no desire if it's completely saturated. So it gets to the point where if there's no oxygen attached to it, then it really, 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 really wants it. And it really grabs and grabs oxygen. Well, as more of your hemoglobin has 3 on it, well, there's less availability. So you're going to have a curve that kind of plateaus near where all 4 are saturated. All 4 oxygen molecules are attached to the spots on the hemoglobin. And we'll look at the curve coming up. So looking at the partial pressure of oxygen in arterial blood, remember partial pressure can be around 100 or 95, but 100 is easier to kind of look at. So this is coming right off of the pulmonary capillaries. So the partial pressure is 100 millimeters of mercury in arterial blood. So there's 20 mils of oxygen per 100 mils of blood. Remember we said 105 is 100% saturated. Partial pressure of 105 is 100%. This is pretty darn close. 5 off is hemoglobin is 98% saturated, meaning 98% of your hemoglobin molecules have 4 oxygen molecules. So even if you're increasing to 105, going up from 100 to 105, you're increasing the partial pressure a little bit. And you're breathing deep, but you're not going to have much of an increase in oxygen percentages binding. You're going to go from 98% to 100%, 2% change. So even if you're taking really deep breaths and you're really trying, you're only going to be able to increase your saturation to 100. In venous blood, the partial pressure of oxygen, we're still talking about that, is 40 millimeters per mercury. So we have about 15 mils of oxygen per 100 mil of blood. Hemoglobin at 40 is still at 75% saturated. That means, again, 75% of your hemoglobin molecules have 4O2. That's when we call it a venous reserve. Oxygen remains in venous blood and we can't get rid of it completely, and it can still be used. That's important because if we're, for whatever reason, not getting oxygen, so we stop breathing, that's why we can have resuscitation, where if you continue to do compression and continue circulation, you have some time where tissues can still get oxygen from this reserve while we're trying to get back breathing and kind of increase circulation. So this is why CPR can be successful, is because we have a reserve of oxygen that can be used if something goes wrong. And once we kind of run out of all of that, well, then there's the difference, but we at least have some time. This is looking at the actual curve. So down here is looking at the partial pressure of oxygen. That's on this side. So we have partial pressure of 20, 40 is going to be at our tissue level, and then 100 is going to be at our lungs. This is looking at our percentage of saturation. So how much of the hemoglobin has the 4 molecules of oxygen? So again, we don't really focus too much on this area because this is going to be our 2 different spots between the tissues and the lungs. At the tissues, again, about 75% of the oxygen is saturated, and at the lungs, 98%. We're almost at 100. This is going to be the difference of what is given to the tissues, unloaded. released from hemoglobin at time. But look at kind of as it's getting towards the 98%, well, there's less of an affinity because there's more hemoglobin that has all what it needs. It can't add more. So it's just kind of like slowly you're running out. Oxygen's waiting for a partner, but you're running out of partners because hemoglobin has its dance partners. Down here, where the partial pressure of oxygen is 20, well, the hemoglobin wants to grab it up as fast as possible until it gets even higher. But then when it's getting towards the 98%, doesn't need it as much. It's old news. Why are we talking about the hemoglobin saturation? Well, this can change based on certain factors. A major one is going to be body temperature. So body temp, which can change not just because of bad things like fever, but just by exercising. When you're moving your muscles, you're creating more heat and your temperature rises. And that's why you start sweating. Also, increased metabolism, then you can have an increased temperature. This is important. So if you're exercising, this is a good example. So what's happening during exercise? Your muscles are contracting a lot. What do they want? They want oxygen. They want oxygen so they can make ATP because ATP is necessary for muscles to contract. So what you're going to do is you are going to decrease hemoglobin's affinity for oxygen. Why? You want hemoglobin to not desire oxygen as much because you want hemoglobin to give oxygen to the tissues. So that enhances oxygen unloading, meaning that you're going to have less hemoglobin saturation at a higher partial pressure. So what we're going to do is the point of if you increase the temperature, like I said, in the muscles, then you don't want your oxygen to hang out with your hemoglobin. That's not helpful to the muscles. You want hemoglobin to release its oxygen more readily. So it's not as attached. It can get rid of it easier. So hemoglobin is going to give off more oxygen in increased temperatures, and you're going to shift this curve that we looked at to the right. So normal body temperature, sorry, using degrees Celsius, but same thing. 38 degrees Celsius is about normal body temperature. So we saw that curve right here. So we're getting towards 100 millimeters per mercury for our partial pressure of oxygen over here because we're getting towards 98% over here. What happens when we're increasing our body temperature? Look at the shape of the curve and look at right here. At a higher temperature, there's less hemoglobin that's fully saturated. Not by tons, but a good amount, where you're going to be more at, this could be, say, this is 100, so this is 92, and this is at 89%. So less hemoglobin has 4 oxygen molecules attached to it. Why? Because it's giving more of its oxygen molecules to the tissues that it needs. And in this case, when you're exercising, it's the muscles and other various, but the major one's going to be muscle. But that's what you want. Your muscles desire more oxygen. So why would you keep it on your hemoglobin when your tissues and your muscles need it? That's the ultimate goal, is to give it to the cells, to give it to the tissues so they can use it. So to increase body temperature, you're going to shift this curve a little to the right. So again, it's going from this way to that way. So eventually, higher partial pressures, you'd match it and get higher and a little higher. But at the same partial pressure, there's more oxygen going to the tissues than there's staying on the hemoglobin. Opposite is true as if you're colder, but we have less kind of options. Usually our temperature's increasing, unless you're jumping in kind of ice water and staying there, then your shift is going to be to the left. Now we're looking at BPG, or 2,3 biphosphogyl glycerate. Glycerate. Can't say that 5 times fast. So you produce BPG when the red blood cells are performing glycolysis. Remember, our BCs do anaerobic metabolism. They don't use the oxygen that they carry. So this is going to be produced during that process. The higher the level of BPG levels, cause more oxygen to be released as well. So if you are increasing oxygen release, then you're shifting the curve to the right again. So what we're having is we're having more red blood cells. They're producing anaerobic metabolism because they need ATP for energy levels too. So you're going to increase its oxygen release. So you're going to decrease the affinity of oxygen to stay with hemoglobin. Hemoglobin's going to release it. Again, shift it to the right. pH is going to be another factor. So we're going to see when we talk about carbon dioxide transport that actually having an increased amount of carbon dioxide in your body is actually going to cause your pH to go down or decrease or become more acidic. Also, if you have lactic acid, acid makes pH decrease. This is also going to shift the curve to the right. Now think about why this would happen. If you have an increase of carbon dioxide, then you're probably having an increase in metabolism, an increase in making ATP. Because remember, carbon dioxide is the waste product. Also, lactic acid accumulates when you have more anaerobic respiration because you're not getting enough oxygen. So both of these conditions, you want more oxygen in the tissues. So it's going to again shift curve to the right. So you have normal carbon dioxide levels. If you increase the amount of carbon dioxide, then you're going to decrease the pH. So look, 7.4 to 7.2. This means, again, that you're doing a lot of activity. So this is active tissues most often, that the tissues need more oxygen. So you are going to, at the same partial pressures, with kind of same partial pressure of 100 here, there's going to be less oxygen on the hemoglobin here because it's going to go to the tissues when you decrease the pH. And then this is normal. If you decrease the amount of carbon dioxide, then you actually shift the curve to the left, where hemoglobin is going to keep its oxygen more. If you have carbon dioxide, some of it actually is carried by the hemoglobin, the oxygen part of carbon dioxide combined to the hemoglobin. As carbon dioxide levels rise, it can push oxygen off of the hemoglobin more readily. Again, this is what we want. If you're having higher levels of carbon dioxide, then most likely you're having more acid too. then you want your tissues are going to need more oxygen because they're producing more carbon dioxide. So this means that they're active. They need more oxygen. So if the tissues need more oxygen, well, push it off of hemoglobin. That's what's delivering it. So you are going to push it off of hemoglobin because you have an increase in carbon dioxide. So that's why we have increased carbon dioxide and then a decrease of pH. So we look at the Bohr effect. As pH decreases, meaning it gets more acidic, and again, most often, a lot of times is carbon dioxide buildup, and we'll see why it's acidic the next video. Hemoglobin is going to give off oxygen more readily. Hemoglobin is less saturated. Why? You don't want oxygen on the hemoglobin. You want oxygen in the tissues because there's more activity. You need more oxygen. Your tissues are producing carbon dioxide because they are making ATP. So you need more oxygen to the tissues so they can do their normal activities in making ATP. Briefly looking at fetal hemoglobin, so this is going to be in utero. So fetal hemoglobin has a higher affinity, meaning a higher desire to attach to oxygen than adult hemoglobin. Why? Think about why this was important. Where is the fetus getting its oxygen? From the female. So it's important for fetal hemoglobin to attach and want that oxygen even more because that's how it's going to get oxygen across the placenta and to its body. It is actually attaching and wanting that oxygen even more. So fetal hemoglobin is going to attach a lot harder to oxygen and keep it, trying to make sure that it can get saturation at lower partial pressures. So this actually shifts the curve to the left a little. So at a lower partial pressure, we're getting closer to that 100% saturation with less amount of oxygen available. But even though there's less amount of oxygen, the hemoglobin's going to grab it up as fast as possible. So hemoglobin's going to grab it, have a higher affinity of sticking to it than the adult hemoglobin. Why is that important? Again, it may have lower partial pressure because it's getting from a female. So it wants to grab up as much as possible so that it can deliver it to its tissues. Some terms when we have issues with oxygen transport. We have what we call hypoxia. General term of there's not enough oxygen that's getting to the tissues. That's the general term. Not enough oxygen to the tissues. But there can be different reasons on why we're not getting enough oxygen to our tissues. You can have anemic hypoxia. So not enough oxygen to the tissues because there's not either enough red blood cells or not enough hemoglobin. So this is a transport issue. So there's not enough trucks to carry the oxygen to the tissues. So, or delivery drivers, you can think of it that way. So if you have less delivery drivers, well, less oxygen can be delivered. So less oxygen being able to be delivered means less oxygen to the body tissues. Ischemic hypoxia, still hypoxia, not enough blood to the tissues, but this is because you blocked the road or slowed down circulation for whatever reason. So if your road is blocked, well, less oxygen can get into that area, so you have less oxygen in body tissues. If you have a slowdown, well, it's going to take longer for the oxygen to get there, and the tissues are going to be deprived of oxygen. Histotoxic hypoxia is actually when your cells can't take in oxygen for whatever reason. And this often happens in cyanide poisoning. So if the cells can't use oxygen, so meaning your mitochondria can't use oxygen to make ATP, well, eventually you quickly run out of ATP and can't make it, and then run out of energy, so everything stops. So can't use the oxygen, your body tissues just realize that it doesn't have enough oxygen because it can't use it. So it's a functional thing. So your once you get the oxygen, you can't use it. And so your cells are still starved of it because it can't be used. Oxygen is still around, but you're not making ATP, and that's the point of oxygen. Hypoxemic hypoxia is actually carbon monoxide poisoning. Oftentimes, carbon monoxide actually has a strong affinity for hemoglobin and kicks off the oxygen. So instead of carrying oxygen to the tissues, it's carrying carbon monoxide. Carbon monoxide can't be used to make ATP. So that's where you get not enough oxygen going to the tissues because carbon dioxide's taking up the space.